So hello everyone, welcome to the channel. So in this video I'm gonna show you tracking air pollution with Sentinel-5P imagery. So nitrogen dioxide monitoring using Google Earth Engine. So now let's get started. So air pollution is a major environmental concern significantly impacting human health and atmospheric quality. Among various air pollutants, the nitrogen dioxide plays a critical role in atmospheric chemistry, contributing to the formation of ground level ozone and particulate matter. So nitrogen dioxide is primarily emitted from the vehicular traffics, industrial activity and combustion processes, making the urban area particularly vulnerable to its adverse effect. So exposure to the elevated nitrogen dioxide level is linked to respiratory diseases, cardiovascular diseases and reduced lung functions, highlighting a need for continuous monitoring and mitigation strategies. So the satellite-based remote sensing offers an efficient and large-scale approach for monitoring nitrogen dioxide concentration. The Sentinel-5P satellite was launched by European Space Agency, provides a high-resolution data on atmospheric pollutants including the nitrogen dioxide, enabling the researchers to analyze the pollution trend over time. So to analyze the nitrogen dioxide concentration for any study region, first we have to define our region of interest. For example, I have navigated to this particular study region called Thailand. So I'm going to create my study region using this tool called draw a rectangle. So once you click that, we have this option here. So I'm going to draw a rectangle over the study region. So once you did that, so we're going to click this option called exceed. So in the top section, we have this new variable called variable geometry. So with polygon F4 vertices indicating the study region. And I'm going to click this option called show generated code. So we have this generated code. So in this variable, we have this latitude and longitude of the study region. So I'm going to copy this latitude and longitude of the newly created study region using Ctrl C in our keyboard. And now we're going to paste this latitude and longitude in this variable called urban coords. So using Ctrl V in our keyboard, Ctrl V. So now I have pasted my the latitude and longitude of this particular study region. So now this particular variable urban coordinates, which holds the latitude and longitude of the study region. Next, we have to convert this variable to a polygon. So to do that, we're going to define another variable ROI equals to earthengine.geometry.polygon urban coords. So now it's going to convert our variable containing the coordinates into a geometry polygon. So in our next step, we have to center this particular layer. So to do that, we're going to define map.center object and mentioning the variable name ROI, that is region of interest, with a suitable zoom level of 5. And next, to add this layer, we're going to define another code called map.addLayer ROI with the default visualization parameter for our study region and output the layer name as study area. So next we have to set our analysis time period. For example, the dataset availability is from 2018 to 2025. So I'm going to set my analysis period from 2019 to 2024 to analyze the nitrogen dioxide concentration over this study region. So we over this defined study region. So this study region contains Thailand, Cambodia and Vietnam. So to specify our time period, we're going to define a variable start year equals to 2019, and similarly we're going to define our end year analysis period. We're going to define a variable end year equals to 2024. Next, to perform analysis, we required our nitrogen dioxide dataset from Sentinel-5P. So for that, we're gonna to access the nitrogen dioxide dataset, we're going to define another variable NO₂ collection equals to earthengine.image collection Copernicus S5P NRTI L3 NO₂. So now let me explain about this particular dataset. The dataset availability is from 2018 to 2025 and the dataset provider is European Union ESA Copernicus, and using this code you can access this nitrogen dioxide dataset. And we have this following bands that is available in this dataset, starting with NO₂ column number density and the units in moles, moles per meter square, and the minimum and maximum value. And the description about this particular band is total vertical column of NO₂, ratio of the ratio of slant column density of NO₂, and the total air mass factor. And we have another band called tropospheric NO₂ column number density and stratospheric NO₂ column number density and NO₂ slant column number density. And we have this variety of different band that is available. So we're going to specifically focus on this particular band called NO₂ column number density. And the units of this particular band is mole per meter square. So to go through the description about this band NO₂ column number density band. So NO₂ column number density band in Sentinel-5P dataset represents the total vertical column density of nitrogen dioxide in atmosphere. It is measured in moles per square meters and is derived from the ratio of slant column density, that is the total NO₂ along the sensor's line of sight, to the total air mass factor, which accounts for the atmospheric scattering and absorption effects. This band provides a measure of how much NO₂ is present in the vertical column of atmosphere above a given location. Hence, the nitrogen dioxide is a major pollutant produced by fossil fuels, combustion, industrial emissions, and biomass burning. This dataset is widely used for monitoring air quality. And the characteristics of this data is the unit is represented in moles per meter square, and the value ranges from negative 0.00006 to 0.0096 moles per meter square. And the lower bound, that is this particular value, represents the extremely low or negligible NO₂ concentration, and this the higher value of 0.0096, which represents high nitrogen dioxide level, typically found in urban areas and industrial zones or region experiencing the biomass burning. So this study, we're going to utilize the Sentinel-5P, and we're going to mention the time period, and we're going to compute time series analysis and visualize the NO₂ with the study region. So let me get back to Earth Engine. So these are the variety of band that is available, and you can go through the description about this band, and the resolution of this band is around 1000 meters. So once you have accessed this Sentinel-5P NO₂ dataset, next in the dataset we have to select the particular band of our choice. For example, we're going to select NO₂ column number density as specified here. So we're going to select this particular band. So to analyze the nitrogen dioxide concentration over the study region. So next we have to filter with the specific timeline. So for that we're going to define another function dot filter date, and we're going to mention the start year and the end year. So start year we have mentioned this variable as 2019, and the end year we have mentioned as 2024. And in the next we're going to generate a list of years and month. So to generate the list of years and month, we're going to define another variable called year list equals to Earth Engine dot list dot sequence and Earth Engine dot number dot parse. So the parse function, using parse function, it ensures the years are treated as a number and avoiding errors when filtering the date-based dataset. So Earth Engine dot list dot sequence, Earth Engine dot number dot parse, and the start year, that is 2019, and Earth Engine dot parse dot number dot parse, the end year, that is 2024, and dot subtract -1. So the period of analysis will be between 2019 to 2023. So let us view that. So here I'm going to mention this variable year list, and let us visualize it. So I'm going to run this code. So now in the console section, you can able to visualize we have our list of year analysis. So starting from 2019 to 2023. So this will be our period of analysis from 2019 to 2023. And similarly, to create a list of months, so we're going to define another variable called month list equals to Earth Engine dot list dot sequence 1 to 12. So 1 to 12 here represents the January to December. So 1 represents January and 12 which represents the December. So now it's going to create a list sequence for each year from January to December. So to view that, similarly we're going to define print. So we're going to paste as a months list. So now we're going to run this code again. I'm going to navigate to the run script and click run. And the console section, you can able to visualize the list of months has generated here. So starting from 1 to 12. so January to December. And our next stage of analysis, we're going to compute the monthly average nitrogen dioxide level for each year. So to do that, we're going to first define this variable called monthly NO₂, that is monthly nitrogen dioxide equals to. So we're going to refer this particular image, that is our Sentinel-5P NO₂ image. So Earth Engine dot image collection year list dot map function year. So we're going to we are creating a loop function. So basically this code loops through each year in the year list and each month in the month list to provide us a nitrogen dioxide level. So inside this loop function, we're going to mention the return month list dot map function month. So now we're going to create a monthly nitrogen dioxide level. So for that, we're going to define a variable monthly image equals to NO₂ collections. So NO₂ collection referring to our Sentinel-5P imagery. And in that, we're going to apply this filter function based filter function. So that is dot filter Earth Engine dot filter dot calendar range. So we're going to apply the calendar range function for the start year. We're going to mention year, that is 2019, and the end year we're going to mention as 2024. So this is start year and end year, and the unit is in year. So now we are applied filtered based on year. Similarly, to filter based on month, we're going to apply again this filter function dot filter Earth Engine dot filter dot calendar range. So to visualize it in calendar range, we are using this calendar range function. So start month, that is January, and the end month is December, and the unit is in months. So now we are filtered based on month. So basically what this code it does is, so for each year month pair, it filters the methane collection and keeping only the images from that year and images from that month. And last, we're going to define dot mean function to compute the monthly mean nitrogen dioxide level. And next, we're going to define another variable called timestamp. So to generate timestamp, this sets the first day of the month as a reference for our time series analysis. So for that, we are defining this variable called timestamp equals to Earth Engine dot date dot from year month day. So year, month, and day. So we're gonna keep this set as the first day of the month as a reference for time series analysis. So we're gonna mention as 1 here, and we're gonna return the monthly image, and we're gonna set the default the system properties. So dot set function system time start, and the timestamp in millisecond for format. And last, we're going to mention this flatten function. So the flatten function is generally used to convert it into a single image collection. So each image represents the methane level for specific month. So in our next step, we have to define the visualization parameter for this particular nitrogen dioxide concentration layer. So to set the visualization parameter, we're going to define a variable NO₂, that is nitrogen dioxide with visualization, equals to, we're going to set the minimum value of 0 and to a maximum value of 0.002. So the minimum and maximum value ranges from this particular value here based on our region of interest. So in this case, I have set the minimum to 0 and to a maximum value of around 0.02. And the color palettes, we are using blue, yellow, and red. So red, which indicates the highest level of nitrogen dioxide concentration, and the blue, which indicates the lowest level. So in the geometry inputs, I'm going to turn this off, this layer. So now you can able to see here. And to add this layer, we're going to define map.add layer monthly NO₂ dot mean function. So we are using mean function in order to obtain the mean nitrogen dioxide image for each month. For example, to acquire a nitrogen dioxide image for particular month, so we have variety of different data for each day. So to acquire a mean nitrogen dioxide for concentration for each month, so we're going to define dot mean function, and dot clip function we are applying based on our study region. So we're going to clip the nitrogen dioxide concentration based on our region of interest, and this is the visualization parameter, and we're going to output as average nitrogen dioxide concentration for the entire time period from 2019 to 2024. So in case if you want to specifically visualize the nitrogen dioxide concentration for particular year, I will be showing in the upcoming in the next set of code here. So that is here. So you can able to see we have extracted the nitrogen dioxide for 2020 to 2020 for this particular year. So to generate time series chart, so we're going to define print ui.chart.image.series. Image collection we're going to mention as monthly in NO₂, referring to this particular variable, the monthly in NO₂. So where we computed our monthly average nitrogen dioxide level. And next, the region is the ROI, this is our region of interest. And reducer, we're going to apply earth engine.reducer mean function. So we are applying the statistical function to acquire mean nitrogen dioxide concentration value. And the scale, so we can mention this 1000 meters. And in order to increase the speed of computation, I have mentioned the scale as 7000 to get a faster result. So you can also mention 1000. And the X property, we can define system time start, that is the times period of a start of an analysis period, that is from 2019. And within this time series chart, we can set different options to our time series chart. For example, we're going to define this function called set options. The title we're going to mention is monthly in NO₂ level from 2019 to 2024. And the v-axis I can mention as NO₂ concentration in moles per meter square. And the h-axis I'm going to mention. So in the h-axis, we mentioned the title is here, and the series we're going to mention the color code of our graph. So I mentioned is red here, and you can also mention the point size, for example. So you can mention this point size. So I've mentioned as 4. And next, to extract the nitrogen dioxide for the specific study for specific year. So in that case, we're going to define another variable, NO₂ 2020 equals to monthly NO₂ dot filter date. So we're going to apply the filter date from 2020 January 1, 2020 December 31st. And to acquire the mean nitrogen dioxide concentration for that particular year, we're going to define dot mean function. So next, to add this NO₂ nitrogen dioxide concentration layer to the map, we're going to define map.addLayer NO₂ 2020.clip. So we are applying clip function. So in order to clip based on our region of interest, and the visualization parameter, so NO₂ vis, we have already defined this visualization parameter, and we can output the layer name as NO₂ 2020. And last, we have to export this image to a Google Drive. So to export this nitrogen dioxide concentration image for 2020 to a Google Drive, so we're going to define export.image.drive image.nitro NO₂ 2020.clip ROI. ROI represents our region of interest. And the description, I'm going to specify as NO₂ 2020 mean, and this resolution of this image is 1000. So based on this dataset has a resolution of around 1000 meters. I've specified my export image as 1000 meters, and the region is ROI, and the max pixel value is 1:10^13, and the folder I'm going to mention is NO₂ analysis, and the coordinate reference system is EPSG 4326 is the coordinate reference system. So now let us visualize our image here. First, I'm going to run this code, and let us visualize our time series chart of NO₂ over the study region, for example, over Thailand, Cambodia, and Vietnam. So you can able to visualize this is the time series chart, and let us visualize it in full screen. So I'm going to click this option here. So the monthly NO₂ levels. So the NO₂ level has the highest during this particular year, that is in April 1, 2023, and the lowest concentration is observed in this month, that is in December 1, 2023. And for example, and the second highest level was observed in this particular year, that is in March 1, 2019, and the lowest was observed in the December. So this similar trend can be observed in the study region. For example, in April and March, we have a higher level of nitrogen dioxide concentration. Comparatively, in November and December, we have this lowest level of nitrogen dioxide concentration, and similar scenario was observed here. So in April it was higher, and in the December it was lower. So you can able to observe the similar trend for this entire time span. So next, let us take a look at the image of this particular study region. So in the layers section, we have 3 different layers, starting with our study region. Next is average nitrogen dioxide concentration for the study region for the time period from 2019 to 2024. The average nitrogen dioxide concentration. This image is an average nitrogen dioxide concentration from 2019 to 2024. So based on this, you can able to visualize we have certain hotspots that is located in towards south western part of the study region, and towards the north eastern part of the study region has red spots, and the few red spots are indicated in the north western parts too and northeastern parts. So let us take a look at this particular image here. So we're going to zoom into this particular area. So this particular area, which is indicated as the hot spot of nitrogen dioxide concentration. So now we're going to turn to a satellite mode here. So you can able to visualize it. So let me turn on the study area. So this is a hot spot over this particular study region. So I'm going to adjust this transparency level. So you can able to see here, based on our transparency, this particular study region is lying over the urban area. So over urban area, the concentration of nitrogen dioxide is pretty higher compared to the other part of the study region. So you can able to see here. So this is a hotspot, and clearly which indicates the Bangkok has a higher level of nitrogen dioxide concentration. So you can able to see that. And so let us visualize the other hotspots too here. So towards the north, the eastern part of the study region. So here you can able to see here we have the higher concentration. So you can able to see here this particular area has a higher level of nitrogen dioxide concentration. So let us visualize any we can find any urban areas in this particular study region. So you can able to visualize here we have this some settlements can be observed here. So we're going to turn off this layer here. So you can able to visualize we have this urbanized areas, and a lot of factories can be observed in this study region. So based on this data here, we have this high level of nitrogen dioxide can be observed over this study region, and similarly over this part of the areas too. So probably which indicates due to the presence of the urban areas, for example. So you can able to observe this different urban structures here, and similarly in these areas you can able to observe the urban structures might causing significant level of nitrogen dioxide concentration in the study region. So let me zoom out. I'm gonna turn on this average nitrogen dioxide concentration. So based on the observation, we can able to visualize over the urban areas we have a higher level of nitrogen dioxide concentration. And let us visualize for 2020. So this is 2020, and this is 20 average nitrogen dioxide concentration over time span 2019 to 2024, and this is specifically for 2020. So you can able to visualize this hotspot emerges for this over this particular study region. So in our next step, we're going to export this image to our drive here. So to export, we're going to navigate to the task option here. And in this, we have this unsubmitted task called NO₂ 2020 mean. So to export to Google Drive, we're going to click this option called run. And now a new window pop up saying initiate image export. So we have this task name NO₂ 2020 mean, the coordinate reference system. So we're going to export to our drive, and we are set to a spatial resolution of 1000. So the drive which represents our Google Drive. So you can also export to a cloud storage and Earth Engine asset. So now we're going to export to my drive here. So to export to a drive, we're going to click this option called drive, and make sure that is selected as a file format as GeoTIFF file format. And to export to a Google Drive, we're going to click this option called run. So now we're going to cancel this. So to export, we have to make sure that you click run. So in this video, we have focused on tracking air pollution. We're using Sentinel-5P, the nitrogen dioxide monitoring in Earth Engine. So the code link will be given in the description of this video. So thanks for watching, and make sure that you subscribe to our channel and give us a like.